medium access in LTE-U, mechanism enhancement, and DTMC modeling. Abstract: to address the challenge of ever-growing data rate demand and benefit from the popularity of Wi-Fi capability in mobile phones, 3GPP is studying techniques which enable the coexistence of Wi-Fi and LTE in the unlicensed band, known as LTE-U flavor of listen before the talk (LBT). Listen before the talk principle, referred to as load-based equipment (ABE) and frame-based equipment (FBE, are recommended by 3GPP. In this paper, we investigate two enhancement FBE mechanisms. For example, first, enhancement FBE, EFBE, and second, back-off and idle time reduction FBE, BITR FBE, for the purpose of improving FBE. After presenting the idea of EFBE, we propose BITR FBE, which can further improve throughput, shorten delay, and reduce the energy consumption of LTE-U or Wi-Fi devices. The performance of these both mechanisms is evaluated through Markov modeling and simulation with respect to throughput, delay, energy consumption, as well as transmission opportunities under both homogeneous and heterogeneous network scenarios. Introduction. With the explosively growing demand for broadband services over mobile networks, the traditional practice of carrying data traffic solely in the licensed band needed to be revisited. Recently, 3GPP decided to embark on the specification of licensed assistance access (LAA) by allowing long-term evolution LTE operate in the unlicensed band (LTE-U). First, our central focus of these studies on LTE-U is fair sharing and coexistence with Wi-Fi. A criterion adopted to ensure LTE and Wi-Fi coexistence is that on LAA devices should not impose strong interference on its Wi-Fi neighbors than other existing Wi-Fi stations do. Accordingly, the listen before talk (LBT) principle is introduced for medium access control (MEC) in LTE-U in order to maintain fair access among devices. Two types of LBT mechanisms referred to as frame-based equipment (FBE) and load-based equipment (LBE) are designed. Second, these two mechanisms allow LTE devices to compete with Wi-Fi stations for channel access in the unlicensed band. Research work regarding both LBT flavors exists. The author in 3 proposed to let all LTE node be sense the medium before transmission in order to operate LTE in a licensed exempt band. In 4, an LTE muting scheme was proposed in which the LTE node B muted some of their subframes to increase Wi-Fi transmission opportunities. A comparison of different coexistence mechanism between LAA and the Wi-Fi networks was performed in 5. In addition to coexistence LAA with other LAA operators, using LBT was considered in 6. In 7, a general model for contention-based MAC protocol was proposed using a single Markov chain, an analytical framework to study a coexistence performance between LAA and LAA devices or among LAA and Wi-Fi devices with a simple LBT scheme was introduced in 8 to improve the performance of FBE. A back-off BO procedure was introduced as enhanced FBE. EFBE 9. However, the performance of EFBE was not investigated therein. Neither is it clear on how FBE or EFBE can be further improved. The observation triggered our motivation for this study, which targets as proposing a mechanism to improve FBE and evaluate the performance of these mechanisms. The LBT principle is considered in original FBE mechanism. Second, by applying clear channel assessment (CCA) Before transmitting, the BU procedure introduced the EFBE achieves better fairness among competing FBE and Wi-Fi devices. 9. In both cases, however, a node which failed in the previous channel access contention has to wait for a necessary ideal time before competing for channel access again. In this paper, we propose a novel backoff and an ideal time reduction FEE, BITR FEE mechanism which is able to achieve shorter access delay and reduced energy consumption. Furthermore, we developed discrete time Markov models to evaluate the performance of both BITR FEE and EFBE and validate the models through simulations under various network scenarios. The remainder of this paper is organized as follows. In Section 2, the network scenario and assumptions are explained. Section 3 and Section 4 outline the principle and the developed analytical model of the BITR FEE mechanism. The performance analysis and the numerical results are presented in Section 5 and Section 6 respectively, before the paper concluded in Section 7. Network scenario and assumptions, EFB and Wi-Fi, LTE-U E node B, Wi-Fi access point, BITR FE Wi-Fi, EFE plus Wi-Fi. A network scenario with coexisting LTE-U and Wi-Fi node. Consider scenario is figure 1, which both Wi-Fi access point and the LTE node B are deployed in an overlapping area. Wi-Fi and LTE-U devices are operated in a licensed 5 GHz band. The LTE-U devices could be configured as either figure to illustrate of the BFE, EFE, and the BITR FE mechanisms. EFE and Wi-Fi and BITR FE and Wi-Fi devices as shown in the figure. The laptop supports Wi-Fi only. Assume that all the mobile phones and laptops are within the coverage of both LTE and Wi-Fi. For analysis convenience, we assume also that traffic follows a poison arrival process. 3. Principle of the BITR FE mechanisms. According to the original FE principle 1 and 2, an LTE-U device started its data transmission if the channel is sensed as ideal for a fixed CCA interval. Its data transmission duration, for example, channel occupied time (COT), is fixed value. Immediately after the COT, a fixed ideal period is needed before the next channel access starts. As illustrated in Figure 2a, in EFBE, an extended CCA, ECCA duration after the initial CCA is introduced by adding a BO procedure before data transmission in order to diminish the greediness of FBE channel access 9. However, EFBE devices which lost channel access competition still has to wait for the same ideal period as in FBE. Before it starts channel sensing again, this step leads to an necessary waiting time for the EFBE devices as depicted in Figure 2b. In this section, we propose a novel approach to further improve EFBE. The main idea of the BITR FBE mechanism is to improve transmission efficiency by eliminating the ideal period after the COT for those nodes which sense the original, which sense the channel as busy. Its principle is shown in Figure 2 to see from the original FE designs. 2. The ideal period is considered for a device to switch from the transmission mode to the reception mode. In BITR FE, however, the ideal period is deleted if a node does not get a chance for its frame transmission. In other words, if a node senses the channel as busy after CCA, it will regard the channel as occupied for a period of the channel occupancy time exactly, instead of the COT plus an ideal period as used FBE and EFBE. The rationale behind this design is that a node which failed is in the previous round of channel access has enough time for mode switching. On the other hand, the node which win ECCA competition and transmit its frame follows the original FBE procedure for its next frame transmission by performing CCA after the ideal period. As a consequence of BITR FBE, the node which failed channel access contention in the previous round could obtain a better chance for transmission in the next round. The COT is one of the critical parameters in the FBE design. This value varies from 1000 microsecond to 10 millisecond according to the 3GPP recommendation. Based on this value, the ideal period also varies since it's calculated the ideal period COT times 0.05. Furthermore, the CCA period is also fixed as 20 microsecond. Correspondingly to works mode synchronous and asynchronous exist when applying BITR FBE by synchronous. We refer to a situation in whether the ideal period minus CCA can be multiplied by an integer number ij with the duration of CCA. For example, assume COT 2000 millisecond, then ideal period 100 microsecond, which is 5 times the CCA duration. In this case, a collision may happen if two or more nodes sense the channel is ideal and select the same smallest BO value for their ECCA. On the other hand, if ideal period minus CCA divided by the CCA duration is not an integer number, BITR FBE works is an asynchronous mode. Under this mode, it is not possible that multiple nodes sense the channel as ideal and then select their BO value for exactly the same time duration. In other words, a node in the asynchronous mode will either transmit a frame or detect that another node is transmitting. Markov model and BITR FBE mechanism. DTMC is adapted to model the behavior of the BITR FBE BO procedure under both working models. As stated in our models, represent the BO value, a node of interest selected for transmission competition, including both back-off and freeze procedures. Considering the BO procedure and transmission opportunities for two competing devices, we develop correspondingly model for homogeneous and heterogeneous network. While only one type of devices exist, in the homogeneous network. A heterogeneous network may consist of a mixture of EFBE, BITR FBE, and Wi-Fi devices. Modeling of homogeneous networks consider that two EFBE nodes or two BITR FBE nodes operate in the synchronous or asynchronous mode. We have developed DTMC models which state the transition for the general case with the contention window, CW, size CW, and where n g. For illustration clarity, we present below only a simple case with two BITR FBE nodes operate in the synchronous mode with CW equal D. Two BITR FBE synchronous node with CW equal 2. When two BITR FBE nodes, namely A and B, compete for channel access in the synchronous mode, the node which is selected. Figure 3. DTMC model for the BITR FBE synchronous with CW equal 2. The smallest BO value after CCA will be the winner and it transmitted its frame. However, a collision happens. Both nodes has the same BO value after CCA in the current competition. Since a node which lost competition in the previous round would freeze in BO's counter, its current BO values depend both on the remaining BO values from previous round and the newly selected value in the current round. Correspondingly, in the DTMC model, the three parameters are required. The first one is the remaining BO position of both nodes A and B, based on that there are three possible conditions, i.e. A is better than B, B is better than A, and A equal B. The other two parameters are the current BO value of the two nodes with a possible value from 0 CW minus 1, as we assume CW equal 2 is example. There are only two possible values, 0 and 1, and shown in figure 3. With these combinations, we have in total 12 states in these models. Among them, there are 4 states in which will transmit, for example, A's CW equal 0 and B's CW equal 0. B is better than A, with A's CW equal 0 and B squares B's CW equal 1. Similarly, there are 4 other states with B obtains channel access. However, a collision happens in 4 remaining states, which are A equal B with A equal CW equal 0, B CW equal 0, A equal B with A's CW equal 0, and B's CW equal 0, as A's CW equal 1 and B's CW equal 0, and A is better than B, and A's CW equal 0, B's CW equal 1. Table probability transition matrix for the BITR FBE nodes operate in the synchronous mode with CW equal 2. The corresponding transition probability matrix P for the case with 2 BITR FBE nodes operating in the synchronous mode is shown in tab 1. Steady state probabilities based on the conditions that calculate the steady state probabilities. Pi 0 equals 0.1177. Following the discussion regarding the probability of node being in the stage of successful transmission, collision, and loss competition, we compute the transmission probability PTXA 0.7017, successful transmission probability PTX collision probability, and modeling of heterogeneous network. Consider a network with a combination LTE-U and Wi-Fi node. Under the heterogeneous scenario, we model one AFBE node versus a Wi-Fi node, and one BITR FBE node versus one Wi-Fi node competing for common channel with different CW size. Due to the page limit, we present only the latter case with general window size of CW equal n. BITR FBE and Wi-Fi with a CW equal n. The general expressions for the state transition probability of matrix P when one BITR FBE node and Wi-Fi node competing for channel access in the common channel with CW equal n are shown in tab 2 below. Table 2 transition probabilities when BITR FBE and Wi-Fi coexistence. In the DTMC model, each state contains 3 parameters. They are the BO values of the BITR FBE node I and the Wi-Fi node J, as well as current BO relationship between the BITR FBE and Wi-Fi node, represented by the A and B respectively. Based on their BO values, their conditions are possible. A is better than B, B is better than A, and A equal B. Depending on the CW size, the size of P varies. Similar to the homogeneous scenario, 3 parameters are considered in each state, and the general expressions for the transition probabilities from one state to another are explained in the table. As an example, with CW, the transition probabilities for node A to transfer from successful transmission state to next possible state are respectively P, A, the same in the homogeneous case. Homogeneous case, we use probability transition metrics to calculate the steady state probabilities where the summation of them are equal to 1. Based on the obtained steady state probabilities from tab 2, we calculate the successful transmission, collision, and loss probabilities PTX, PTSS, PC, and PL of the BITR, FBE, and Wi-Fi nodes according to the expression shown in tab 3. Transmission probabilities when BITR, FDE, and Wi-Fi coexistence. Performance analysis. The parameters we adopted for the evaluating the performance of the AFBE, BITR, FBE mechanisms are average cycle length, delay, network throughput, and transmission average consumption explained below. Average cycle length. The average cycle length is a parameter which reflects the delay of an access mechanism, including both channel access delay and the frame transmission delay. We calculate the duration of each transmission cycle and obtaining the sum of all cycle period over the observation time. In both AFBE and BITR FBE, each transmission cycle state starts with the initial CCA phase. If the channel is sensed as idle, the procedure continues with the ECCA phase, depending afterward on the channel availability status, data transmission, COT over or other ongoing transmission happens. For EFE, the transmission cycles ends up with the ideal period. In the BITR FE, however, a cycle terminates immediately right after COT phase or phase for those nodes which lost access competition. Depending on the selected BO value for each ECCA and the status of the previous contention, the cycle length CI differs from one cycle to another. Therefore, we divided the total cycle length by the number of cycles H occurred during the observation time in order to obtain the average cycle length as expressed in expressed 1. Network throughput. For the calculation of the network throughput, we assume that each node transmits in a transmission cycle one frame with the ideal packet size of L byte, including the acknowledgement message. Correspondingly is calculated by including the total number of bits transmitted by the participant within an average cycle length of T. To calculate the number of bits transmitted by all participants, we need to know the successful transmission probability of each node for all nodes within the networks. Based on obtaining successful transmission probability from section 4, we obtain general expression to calculate the network throughput of a network with m member of node as follows. Transmission energy consumption. To calculate the energy consumption for AFBE or BITR FBE node, two conditions have to be considered. For example, a node wins the channel access competition or not. Based on the conditions, the energy consumption for each node is calculated as follows, where PCCA and TCCA represent the power consumption during CCA and the CCA duration. The other symbol in 3 are self-explanatory. When calculating Wi-Fi node energy consumption, there are 3 conditions which need to be included. The first condition is that the Wi-Fi node successfully transmitted its frame. The second is that the Wi-Fi node lost contention when competing with EFBE nodes, and the last condition is that the Wi-Fi node fails when competing with BITR FE node. The energy consumption of the Wi-Fi node under those 3 conditions is expressed in 4, where PIDIPS and TDIPS represent the power consumption and time duration of distributed coordinate function interframe space, DIFS. PCCA TDIFS PBO TBO PTX TTX PDIPS dot TDIPS. The total energy consumption E for transmitting section of P packet per FBE, BITR FBE, or Wi-Fi node can be therefore calculated from the following general expression. Numerical result and discussions. In this section, we validate analytical modeling using MATLAB-based simulation for both homogeneous and heterogeneous network. Then we compare the performance of EFBE and the BITR FBE mechanisms while coexisting with Wi-Fi. The parameters mentioned in section 5 are configured as H equal 100 cycles, L equal 114 bytes, and Q equal 100 packets respectively. The power consumption values used for energy calculate are listed in tab 5. Furthermore, the other parameters needed for performance evaluation are configured as TCOT 1000 microsecond and TDIPS 34 microsecond and T-slot 9 microsecond respectively. The simulation results are the average values based on 100 simulation runs. A performance evaluation for homogeneous network. Model validation. Consider that two BITR FBE node A and B coexist in a network with CW equal to for TCOT 100,000, 1,000 and 800 microsecond. We have T ideal TCOT times 0.05 equal 50 or 40 microseconds respectively. Since 50 microseconds divided by the TCCA is not an integer number, while the latter case is both nodes are working either in asynchronous mode with TCOT 1000 microseconds or in the synchronous mode with TCOT 800 microseconds. As illustrated in tab 5, numerical result for PTX, PTXS, PC, and PL obtained based on the developed DTMC model and simulations match with each other. Therefore, the correctness of the model is validated. If it is further observed from the table that the obtained collision probability is 0 when the network is operated in asynchronous mode. This is because it is not possible that both nodes observe the channel and ideal and selected the same BO values after ECCA when they are operated in the asynchronous mode. Under the asynchronous mode, the collision probability is very high since configured CW size is very small. With a large CW, PC will be reduced significantly. Another observation from this table is that fair access is achieved in homogeneous networks. Performance evaluation. The obtained network throughput, delay, and energy consumption for both modes and then illustrated in tab 3. From these results, we observe that higher network throughput is achieved in the asynchronous mode. This is because that the collision which happened in the asynchronous mode have a negative effect on network throughput. For this reason, the energy consumption in the synchronous mode is lower.